name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about engineering electrically switchable quantum anomalous Hall states by spin orbit coupling. It was written by Moson Queen and also Kim Watanabe and Tokoshi Tanguchi. Simon and also Polishin, and it was written by the Institute of Science and Technology Austria and also Center for Theoretical Physics, Central Laboratory, Park Road, Oxford, and National Institute for Material Science, and also Material Science was Namiki in Japan and UK. Non-volatile gate-driven switching of quantum anomalous Hall or QAH states in graphene-Moiri systems provides a promising road to wide topological electronics based on chiral edge states. However, deliberate use of this switching mechanism requires control over both the magnetic properties and meta stability of QAH or quantum anomalous Hall. While previous demonstrates mostly relied on the intrinsic magnetic energy landscape of more devices, here we show that this landscape can be engineered through proximity couplings to WSE2. We find that the proximatizing twisted monolayer by layer graphene by WSE2 reshapes the magnetization reversal responsible for non-volatile electrical switching of QAH or quantum anomalous Hall. We attribute this effect to the proximity-induced spin-orbit coupling or SOSC, which can lock a spin and valley and modify the magnetization of the competing states involved in switching compared with non-proximatized graphene systems of finding established proximity-induced SOC or spin-orbit coupling as a new way to engineer magnetic properties and switchable magnetic states in graphene-based system. We further demonstrate that strong magnetic metastability in TMBG allows the magnetic states to be gauge-tuned between QAH or quantum anomalous Hall and metallic regimes, and between QAH states with shared numbers with absolute share is equal to 2 and 1 without resetting the magnetic state. This functionality points toward new device architectures based on QIH chiral edge states. In zero magnetic field, QAH states are bistable between two magnetic states that have the opposite shear numbers and opposite edge state chiralities. The ease of electrical readout through the sign of the quantized Hall resistance and the absence of a strong magnetic field requirement make quantum anomalous Hall states promising for applications in the metrology, low power magnetic memory, in memory computing, microwave devices based on the reconfigurable edge states, and hybrid quantum anomalous Hall superconductor devices. Realizing these applications, however, requires efficient and non-volatile control of quantum anomalous Hall states, motivating recent efforts to manipulate these states electrically and optically. Gate voltage driven non-volatile electrical control is particularly attractive because it could enable low dissipation operation and dense electronic integration. It is also highly desirable to extend gauge control from mere switching of the sign of the share number to turning between distinct share numbers or metallic phases, as this enables new operation modes for potential devices. The orbital character and high-gauge tunability of magnetism in Grafen-Moiri systems enable a distinct form of non-volatile gauge-driven switching of the magnetic and quantum anomalous Hall states. This switching exploits regimes in which the magnetization changes sign as a function of chemical potential or displacement field, both of which can be controlled by electrical gating. Non-volatile switching is achieved by electrically tuning the system across such a magnetization reversal, thereby reversing the stability of the magnetic states in a small external magnetic field. MR or magnetization reversal can commonly occur with the quantum anomalous Hall play to when the chemical potential crosses the Chern gap, resulting in a rapid change and sign reversal of the orbital magnetization. Such behavior has been observed in twisted monolayer bilayer graphene, twisted bilayer graphene, and rhombohedral graphene multilayers. However, MR or magnetization reversal can also occur in metallic regimes and even in systems without superlattices. The ability to tune the magnetization and metastability of quantum anomalous Hall and related metallic magnetism states is crucial for the efficient control of quantum anomalous Hall states. How these quantities can be purposefully engineered, however, remain largely unexplored in graphene systems. Spin-orbit coupling or SOC provides a natural route to controlling magnetic properties in two-dimensional systems because it couples spin and orbital degrees of freedom. Auto-intrinsic spin-orbit coupling in graphene is weak. Proximity to transition metal dichalcogenide or TMDs can induce SOC of up to several megaelectron volts. In graphene Moir systems, proximity to TMDs or transition metal dichalcogenides has previously been demonstrated to stabilize superconductivity at ferromagnetic states. Here we show that proximity-induced SOC modifies the magnetization, reversal behavior, and non-volatile electric switching of QAH states. To this end, we investigate QAH states and magnetism in TMBG devices proximatized by either a monolayer or bilayer of WSE2, which we refer to as TMBG per WSE2. We investigate 5 TMBG per WSE2 device, D1 to T5, with twist angles in the range when the theta angle is almost between 1.1 to 1.5 degrees. In all these devices, WSE2 is placed on the Bernal bilayer side. The band structure calculations indicate that this placement of the WSE2 layer induces a stronger SOC at D is less than 0 in the valence band and at the D is greater than 0 in the conduction band. With the QAH and correlated metallic states observed in the latter regime, the presence of proximity-induced SOC is confirmed by the measurements of quantum oscillations. Similar to TMBG devices without WSC2, TMBG per WSC2 devices exhibit correlated metallic and gapped states as partial fillings of the conduction band for D is greater than 0. Measurements of longitudinal resistance and Hall resistance which is RX6 and RYX in devices D2, D3, and D4, which temperatures between 1.2 and 1.4 degrees reveal a large region of metallic isospin, spin, and valley. Ferromagnetic states surrounding an insulating state at Maury superlattice filling when the nu is equal to 2, as highlighted by the RYX data. Two smaller packets of distinct metallic isospin ferromagnetic states are centered near nu is equal to 1 and 3. Devices T2 and T3, which twist angles theta is equal to 1.23 degrees and 1.32 degrees, show quantum anomalous Hall states as nu is equal to 1 and 3. Despite the overall superficial similarity to non-proximatized TMBG, the studied TMBG WSE2 devices exhibit several distinct features: well-quantized QAH states, and an additional magnetization reversal in a metallic state. Nu is between 1 and 2, and the third one is that the absence of such a reversal near nu is equal to 3. So there are two figures. The first figures that you see is layered by the quantized anomalous Hall. The figure one illustrates quantized anomalous Hall or QAH effect in the TMBG WSE2 device, with theta is equal to 1.23 degrees. The D2 schematic of a TMBG per WSE2 device consisting of rotationally misaligned monolayer graphene and Bernal stacked bilayer graphene placed on a monolayer WC2 encapsulated by hexagonal boron nitride, top and bottom graphite gate, control carrier density N, and displacement field D. The B part of this figure calculated band structure of TMBG WC2 with proximity induced easing a spin orbit coupling of lambda 1 is equal to 4 mega electron volt at D is equal to zero point 0.3 and 0 and minus zero point 0.5 volt per nanometer. The section C illustrates longitudinal resistance Rx6 measured in the conduction band at 50 megatesla and D is greater than 0. Sharp dips in the Rx6 at nu is equal to 1 and 3 mark quantized anomalous Hall states surrounded by higher resistance metallic isospin ferromagnetic regions. The section D and E illustrates Hall resistance Rxy measured as a function of temperature T and displacement field D at B is equal to 100 megatesla for nu is equal to 1 and nu is equal to 3 respectively. Dome shaped, as you see in the last one, you see dome shaped regions which Rx y is almost equal to minus h divided by 2 to the e to the power of 2 mark stable and absolute c is equal to 2. Quantumized anomalous Hall states, and this figure magnetic field dependence of Rx and Rx6 star measured at nu is equal to 1, D is equal to 0.48 volts per nanometer, and nu is equal to 3, D is equal to 0.42 volts per nanometer, showing QAH hysteresis. Antisymmetrized Hall resistance Rx measured as a function of n and d near nu is equal to 3 at b is equal to 50 megatesla, showing a qua- quantized anomalous Hall plateau and the derivative of Rx star based on the n measured as a function of an n and d near nu is equal to 3 at b is equal to 50 m Tesla. Their derivative highlights featureless regions of cleavage state transport with decoupled edge states and bulk transport and sharp peaks at plateau transitions due to defect-mediated edge state coupling. As schematically shown in the insets, the derivative of the Rx6 star was measured by sweeping the bottom gate at fixed top gate voltage corresponding to D is equal to 0.41 volt per nanometer. Figure 2 illustrates magnetization reversal and non-volatile electrical switching near nu is equal to 1 quantized anomalous Hall state in device D2. R and B are X R and Rx6B as a function of n and d measured as b is equal to zero point 0.5 Tesla. The fast C axis is n with direction indicated by arrows. In addition to QAH state as nu is equal to 1, a sharp change of the resistance at the intermediate filling near V nu is equal to 1.2 until 1.3. Mark voltage-induced switching between magnetic states. Section C illustrates magnetic hysteresis of Rx measured at D is equal to 0.47 volts per nanometer and N is equal to 1.40, 1.36 and 1.32, 1.08, 0.96, 0.93, 0.89 multiplied by 10 to the power of 12 1 per square centimeter as indicated in A. Curves are offset and scaled for clarity as indicated. Drxy measured as a function of b at d is equal to 0.47 volt per nanometer for opposite and sweep directions as indicated in the left and middle subpanels. The right subpanel shows the difference delta Rx between the two measurements. Dashed straight line mark the slopes expected for states which share number c is equal to positive negative 2 solid and dashed hyperbolic lines near the transition are guide to the eye following b almost is equal to 1 divided by n minus nrf when nrf is the carrier density corresponding to the magnetization reversal point. A non-volatile gate-driven switching of the nu is equal to 1 quantized anonymous Hall states measured by at b is equal to minus 23 Tesla. Red and blue traces correspond to the forward and backward scans of n respectively. The dash trace is a scale difference delta Rx multiplied by 25 between forward and backward sweeps. F and G schematics showing the evolution of magnetization as a function of chemical potential for the two states involved in gate-driven switching. The magnetization reversal point at nu is equal to 3 in TMBG device is removed by spin valley locking induced by easing SOCG. Now I want to go through the quantized anomalous Hall effect in TMBG per WSEG SE2 device D2 quantized anomalous Hall states as filling nu is equal to 1 and 3 are visible as sharp dips in the longitudinal resistance Rx6 in figure 1c. A small magnetic field of 50 megatesla is applied millitesla is applied during these measurements to suppress domain formation and random switching due to biostability. Measurements of Hall resistance Rx as a function of temperature T and displacement field D reveal dome-shaped stability region of the quantized anomalous Hall states marked by Reg as almost is equal to minus 0.5 H per e to the power of 2. The maximum onset temperatures are about 3.5 Kelvin and 6 Kelvin for nu is equal to 1 and 3 respectively compared to those reported in TMBG devices with similar twist angle but without WSC2. Both quantized anomalous Hall states show magnetic hysteresis which Rx erect close to the quantized value for the quantized anomalous Hall state at nu is equal to 3, which has larger gap as evidenced by its higher onset temperature. The zero field absolute RX remains within 0.5% of zero point 0.5 h per e to the power of 2. This robot's quantization is reproduced across all three pairs of hall contacting along the device channel. Moreover, the resistance measured in the configuration RX6 star. See the figure 1, section F, which is topological equivalent to the longitudinal resistance, is nearly zero. Such well-quantized anomalous Hall states were not previously observed in TMVG devices, likely because of the residual twist angle disorder. In contrast, device RD2 is highly homogeneous with twist angle variation delta T is less than 0.02 degrees across the device, as evidenced by two terminal resistance measurements from different contact pairs. This homogeneity is likely aided by the use of WSC2 as substrate and by the improved fabrication procedures methods. A quantized plate is a defining hallmark of a quantum Hall state arising from the interplay between topological edge transport and the disorder induced localization. For the quantized anomalous Hall state at nu is equal to 0, we observe the robust quantized platude as a function of both n and d. When measured as a function of magnetic field and carrier density, RX6 star shows a linear in field shift of the platude position in n consistent with the Strada formula behavior for quantized anomalous Hall which is share number is equal to positive negative to the derivative of Rxx star based on the n plotted over a smaller range of n and b highlights the structure of this plateau. Outside the plateau, Rxx star exhibits slow variations, whereas inside the plateau the signal is nearly featureless apart from the small noise. This behavior confirms transport dominated by chiral edge states and negligible bulk contribution. Typically, Hall apoptose breakdown is associated with a disorder driven localization delocalization transition in which a percolating conductive path connects the opposite ends of the device. In our device, the pellicle is flanked on the both sides by intermediate regions containing sharp peaks closely spaced, and these peaks disperse with magnetic field with the same slope as the quantized and with Hall state consistent with the Strada formula for a C is equal to 2 Shen insulator. They disappear above 1 Kelvin and are replaced by a finite resistance at a temperature much lower than the QAH onset temperature. Given the micron scale device dimensions comparable to the length scale of twist angle disorder, this feature likely have a mesoscopic origin involved individual defect. Indeed, the peak spacing corresponds to adding only a few electrons to the device region between their leads, suggesting that the peaks arise from single electron charging of individual defects. This interpretation is consistent with previous observation of defect charging in graphene Moiri system and near superlattice insulating and field-induced Shen insulating states. Our findings show that the Moiri disorder defects can interfere with clean edge state transport, posing an additional challenge for a mesoscopic device with quantum point contact. Now I want to go through the magnetization reversal. We find that the TMBG pair WC2 devices exhibit a new magnetization reversal in the metallic regime between the quantized and limits Hall state at nu is equal to 1 and insulator at nu is equal to 2. In device T2, D2 several signatures indicate the presence of this reversal. First sense of the magnetic histories in RY exchange near nu is almost equal to 1.25, accompanied by a strong increase in the core C field, indicating that the magnetization crosses zero and changes sign. Second, carrier density sieves show strong hysteresis with two magnetic states characterized by distinct Hall resistance at higher fields. The N-hysteresis is narrow and centered near nu is equal to 1.25, but it rapidly broadens as B approaches zero, eventually spanning the range between nu is almost is equal to zero point 0.8 and 1.6. This hysteresis response enables non-volatile electric switching of the nu is equal to 1 quantiles and limits Hall states. Together, these observations establish the presence of the MR or magnetization reversal alongside magnetic field and carrier density studies, which are universal features of magnetic reversal switching. The magnetic reversal switching is also accompanied by the additional features that likely have a mesoscopic origin, as shown in Figure 2. Part A and B sharp chains in both Rx6 and Rx appear over a narrow range of carrier density near the um, magnetic reversal. We attribute these features to an intermediate state in which a domain wall is trapped between the measurement slits, likely stabilized by residual disorder or device geometry. This interpretation is consistent with the strong contact dependence of these features. Domain walls stabilized by higher magnetic fields are also likely to be responsible for the fine structure observed in Figure 2, Part C, near nu is equal to 1.25 and absolute B is greater than 2. So thank you so much for watching my tutorial video until the end. Today is 16th of June 2026 and time is 10:53. Also, if there is any simulation for this article, you can find it from my github.com/mahsoscript. Also, there is another GitHub, which is github.com/akashi script.